Hi, I'm Jeff Groh, and this is Differential Equations, Lecture 9. Today we're going to talk about Laplace transforms. A Laplace transform is a type of integral transform, of which there are several. The Laplace transform applies to functions that map a domain containing numbers from 0 to infinity into the real numbers. It's defined by the Laplace transform of f. It's going to take in a function of, say, t, and output a function of s. We sometimes just denote this by L of f. It is, by definition, the integral from 0 to infinity of e to the minus st f of t dt. Before getting to examples, I want to talk a little bit about notation. It is common to write the Laplace transform of a function as a capital F, whereas the original function is expressed by lowercase f. This contradicts an earlier convention that capitals represent antiderivatives of lowercase letter functions. Not so here. In this case, capitals represent Laplace transforms of those functions. And so you have one notational convention with two distinct meanings. In this context of Laplace transforms, capitals represent the Laplace transform and not the antiderivative. Now let's do some examples. Consider the function f of t, and it's identically equal to 1. The Laplace transform of that function, or the capital F, will be the integral from 0 to infinity of e to the minus st 1 dt. An antiderivative here, technically, we should write this as the limit as L goes to infinity, where we replace infinity here by the number L. In the future, I'm just going to assume that you know that there's a limit involved, and we'll write this without writing the limit. Antiderivative is negative 1 over s, e to the minus st evaluated from 0 to L. If you plug in the L, and then take the limit as L goes to infinity, if we assume that s is positive, this term will go to 0. We subtract what we get when we plug in 0. The Laplace transform is then 1 over s. We've just shown that the Laplace transform of 1 is 1 over s. The next example that I would like to do is just the function f of t equals t. The Laplace transform then will be the integral from 0 to infinity e to the minus st t dt. To calculate the integral, name the method. This is clearly an integration by parts problem. We need to take a derivative of this t. We'll use the tabular method. We take derivatives down the first column. We have 1 followed by 0. That's where you stop. Integrating down the second column, we get negative 1 over s, e to the minus st, and then 1 over s squared. e to the minus st. We multiply down diagonals, alternating signs, plus and minus. This gives us negative t over s, e to the minus st, and then we subtract 1 over s squared, e to the minus st. Keep in mind, since the integral is an improper integral with one limit of integration equal to infinity, we technically should be doing a limit here as t goes to infinity. We will assume that s is positive so that the integral converges. And if we do that, then you can see that as t goes to infinity, the exponential functions will decay to 0 faster than this will go to infinity here, driving the whole thing to 0. We subtract what we get when we plug in 0. When we plug 0 into the first term, we get 0. When we plug it into the second term, we get negative 1 over s squared, and so we get 1 over s squared. We've now seen that the Laplace transform of the function t is positive 1 over s squared. I bet you can guess what the next example is. I want to calculate the Laplace transform of t squared. Before we do this computation, I want you to make a guess. See what you think it is. By definition, which is the only thing we have to go on right now, we integrate from 0 to infinity e to the minus st t squared dt. Now, this is obviously another integration by parts. We'll use the tabular method again. We'll have t squared e to the minus st, 2t, 2, and 0. That's where you stop. Here we get negative 1 over s e to the minus st, 1 over s squared, e to the minus st, and negative 1 over s cubed, e to the minus st. Multiplying down diagonals and alternating signs, plus, minus, and plus, we obtain negative 1 over s, e to the minus negative t squared over s, e to the minus st, minus 2t over s squared, e to the minus st, and then minus 2 over s cubed, e to the minus st, evaluated from 0 to infinity, and of course we'll assume that s is positive so that the integral converges. In the limit now, as t goes to infinity, the exponential decay will beat out the polynomial growth, and we'll end up with the limit being 0. We'll subtract what we get when we plug in t equals 0. The first and second terms go away. We're left with negative 2 over s cubed, which gives us positive 2 divided by s cubed. We've just shown that the Laplace transform of t squared is 2 divided by s cubed. Let's do this one more time. Might be instructive. The question is, what is the Laplace transform of t cubed? I want you to make a guess. The Laplace transform of t cubed should be the integral from 0 to infinity of e to the minus st t cubed dt. Yes, once again, this is integration by parts. We'll use the tabular method, of course. To calculate the Laplace transform of t cubed, integrate from 0 to infinity e to the minus st t cubed dt. Using the tabular method of integration by parts, we have t cubed and e to the minus s t. This gives us 3t squared, 6t, 6, and 0 down the first column. In the second column we integrate, so we get negative 1 over s, e to the minus st, 1 over s squared, e to the minus st, negative 1 over s cubed, e to the minus st, and positive 1 over s to the fourth, e to the minus st. Multiply down diagonals and alternate signs, plus, minus. And we have minus t cubed over s, e to the minus st. Then we get another minus 3t squared over s squared, e to the minus st. We get yet another minus 6t over s cubed, e to the minus st, and finally yet one more minus 6 over s to the fourth, e to the minus st, and of course we're evaluating as t goes from 0 to infinity. Taking the limit as t goes to infinity, again of course assuming that s is greater than 0 so that the integral converges. The polynomial growth is overwhelmed by the exponential decay, yielding a limit of 0, and when we plug 0 in, the first three terms go away, and we're subtracting 6 over s to the fourth. The answer is 6 divided by s to the fourth. In light of all of these computations, I want you to think about a theorem. What is the Laplace transform of t to the power n? We know that we get one higher power for s in the denominator in each and every single one of these cases. In the numerator, though, we end up with n factorial. Now, this represents not just one equation, it represents a sequence of equations where n takes values in the set of whole numbers. To prove this requires a proof technique that allows us to prove an infinite number of statements in a finite amount of time. The classic method for that is math induction. Math induction is a proof technique where you have an infinite sequence of theorems that you would like to prove. They're like dominoes. You line them up so that if the first one is proved to be true, its truth will knock the second domino over, and it will make that proposition also true. And the truth of that second proposition then will knock over the third domino, making the third proposition true, and so on. All of the propositions are true if you can do two things. First, proposition 1 must be true. Second, we need to prove that the truth of the nth proposition implies the truth of the next proposition. This is the domino trigger. It shows that if one domino falls, then the next domino must also fall. Still, you have to prove that the first domino does in fact fall. And if you do these two things, then you can prove that all of those propositions are true. And that's what we're going to do here. We begin with the n equals 0 case, which is already complete. We've shown that the Laplace transform of t to the 0 is 1 over s. That is 0 factorial over s to the 0 plus 1. And so the n equals 0 case is true. The first domino has fallen. For the next step, you assume that the proposition is true someplace. Not every place, but someplace. I'm going to denote that someplace by n hat. And this is for not all n hat, but for some n hat. That is an element of the set of whole numbers. What we want to show, and when I write WTS, that's a standard mathematical abbreviation for want to show? We want to show that as a logical consequence of this truth, the next proposition must also be true. So we need to show that this truth follows from this one. I should mention that this equation, the assumption that the nth proposition is true, is called the induction hypothesis. So we begin with the Laplace transform of t to the n hat plus 1. The only thing we have to go on is the definition of the Laplace transform. And so we'll write that as the integral from 0 to infinity of e to the minus st t to the n hat plus 1 dt. The method of integration is, as it has been, integration by parts. So we're going to do this one the old-fashioned way. We're going to set u equal to t to the n hat plus 1, and dv is everything else, including the differential. It follows then that du is n hat plus 1 t to the n hat dt, and v is negative 1 over s e to the minus st. This is kind of a side computation, so we'll put this into a box to separate it from everything else. You always do uv and then minus the integral of v du. So we will get minus t to the n hat plus 1 over s e to the minus st, and then we subtract the integral, and this is evaluated from 0 to infinity. We subtract the integral, evaluated from 0 to infinity, of v du. Some of these constants can come out. So the n hat plus 1, the minus, and the s can all come out. We end up with e to the minus st, t to the n hat dt. On the first term, taking the limit as t goes to infinity, again, assuming that s is greater than 0, the exponential decay will beat the polynomial growth, and we'll get 0. When we plug in 0, we also get 0 because of the polynomial factor here. That just leaves us the integral that comes next, n hat plus 1 divided by s. But the rest of it is the Laplace transform of t to the n hat. It's at this point that we apply the induction hypothesis. The induction hypothesis told us exactly what the Laplace transform of t to the n hat was for some n hat, not for all, but for this particular n hat. And on this particular n hat, it gave us n hat factorial divided by s to the n hat plus 1. If we combine what's left over, we're going to get n hat plus 1 factorial divided by s to the n hat plus 2, and that is what we wanted to show. We deduce by the principle of mathematical induction that the Laplace transform of t to the n will always be n factorial divided by s to the n plus 1. And that is the end of the proof. Okay, so I dragged you through an entire proof by mathematical induction. It's important for you to see these kinds of proofs every once in a while, because proof by math induction is one of the standard tools in the mathematician's work chest. You need to have it in your work chest too. Mathematicians, when they publish papers that use mathematical induction, normally don't include the entire proof. And the reason they don't is that this technique is so trivial that every mathematician worth their salt knows how to construct a proof by mathematical induction. It needs to be something that you need to be aware of and to understand and to know how to use at appropriate times. In our next example, I want to calculate the Laplace transform of e to the at. Now, again, we have nothing to go on here but the definition of the Laplace transform. So we'll write the integral from 0 to infinity e to the minus st e to the at dt. We now can combine those exponents. We'll write it as e to the minus s minus at dt. When we add the exponents, I'll factor the negative out of the two terms. You can see that we'll get the negative st and a positive at if we distribute. The integral here is going to be negative 1 over s minus a e to the minus s minus at evaluated from 0 to infinity. This won't converge unless we assume that s is greater than a. In that case, when you take the limit as t goes to infinity, this exponential of k drives everything to 0. And when you plug in 0, you'll get minus a negative 1 over s minus a, which simplifies to just 1 over s minus a. Note that if a is equal to 0, we're taking the Laplace transform of a function that is identically 1. And in that case, it reduces to the result that we had before, 1 over s. As you might guess, we have to calculate the Laplace transforms of a broad array of functions that represent the typical solutions that we have been seeing for our differential equations. For our next example, I would like to do the Laplace transform of the sine of b times t. To do this, again, we appeal to the definition of the Laplace transform. E to the minus st sine of bt is the integrand of an improper integral. Name the method. If you guessed that we need to use integration by parts twice, get what we started with, move to the other side, and divide by a coefficient, you were right. Let me show you how to do this in a way that maybe you wouldn't have thought of before. I would like to do this using the tabular method. To do this, we'll set u equal to either of these two factors. It really doesn't matter which. And dv is everything else. Now we differentiate down the first column, so we'll get negative s e to the minus st, and then s squared e to the minus st. And when we integrate here, we'll get negative 1 over b cosine of bt, and then finally negative 1 over b squared sine of bt. Since we have sine here and sine here, this is where we stop. We're going to multiply down diagonals and alternate signs. We'll subtract the product, the integral of the product in the last row, and alter that by the minus sign on the previous level. This gives us negative 1 over b e to the minus st cosine of bt. On the next row, we get minus a negative and yet one more negative. That's 3 negative signs. So it's going to be minus s over b squared e to the minus st sine of bt, but then we have to subtract the integral of the product, which has a negative, that's 2 negatives so far, and affix a minus sign from before. So all of this was evaluated from 0 to infinity. Here we're subtracting the integral from 0 to infinity. It's going to be s squared over b squared e to the minus st sine of bt dt. The s squared over b squared can come out. So this will come out of the integral. Now, on the first part, when we send t to infinity, the exponential decay will drive everything to 0. When we plug in 0, though, the second term goes away, but the first term does not. We end up with something coming out of here. What we have here is the original integral is now equal to, again, 0 when t goes to infinity. We subtract what we get when we plug in 0. We're going to get a negative 1 over b here on this first term, the second term going to 0. That's minus s squared over b squared times the original integral. All we need to do is send this term to the other side, combine those two terms, and divide by an appropriate factor to solve for the original integral. This gives us I times 1 plus s squared over b squared equals 1 over b. This gives us then that the integral is 1 over b, and down here in the denominator we'll divide this off. We'll have 1 plus s squared over b squared. We merely need to simplify this. When we're adding fractions, we need to have a common denominator, so we'll write this as b squared over b squared. We'll have s squared plus b squared over b squared. We can cancel one factor of b. When we divide a fraction like this, 1 divided by the fraction, we end up just taking the reciprocal. We get b divided by s squared plus b squared. We have then that the Laplace transform of the sine of bt is b divided by s squared plus b squared. And you are just going to memorize this. One thing that might help is to note that sine is an odd function, but as a function of s on the right-hand side, the Laplace transform of sine is an even function because of the square. We need to be able to calculate the Laplace transform of a number of different functions, but to do that, we're going to proceed by writing a bunch of theorems. First, the Laplace transform is a linear transformation. That means that the Laplace transform of f plus g is the Laplace transform of f plus the Laplace transform of g, and also the Laplace transform of a constant times f is a constant times the Laplace transform of f. These properties follow immediately from the linearity of the definite integral. Oops. For example, if I take the Laplace transform of some polynomial, like t plus 4t cubed, by the linearity property, that's the Laplace transform of t plus 4 times the Laplace transform of t cubed. That's going to be 1 divided by s squared plus 4 times 3 factorial divided by s to the 4th. To proceed with the development of the theory, we need some definitions. You may have seen some of these definitions before. We say that a function f has a jump discontinuity at x equals a if, first, the limit as x goes to a from the left and the limit as x goes to a from the right both exist but have different values. So the picture is like this. You have the function going to one value on the left of a and a different value on the right. In that case, the function is said to have a jump discontinuity at x equals a. Next, a function f is said to be, STB is a standard mathematical notation for said to be, piecewise continuous on a closed and bounded interval AB if f has at worst a finite number of jump discontinuities on the interval AB. The discontinuities may also be removable discontinuities where the limit on the left and the limit on the right exist, but the function value is different. That's permissible. If f has a finite number of jump discontinuities or removable discontinuities on that interval. So it can have more than one discontinuity, but they can't be worse than a jump discontinuity. It, for instance, can't have a vertical asymptote at any point within that domain. You may have seen those two definitions before. I would like to produce one you may not have seen before. A function f is said to be piecewise continuous, again, but this time on some interval a to infinity. It will be piecewise continuous on some unbounded interval a to infinity if for each t bigger than a, f is piecewise continuous on the closed and bounded interval 0 to t. This means that it may have, on the interval 0, say a to infinity, an infinite number of jump discontinuities. It just can't have an infinite number of jump discontinuities on any finite interval. So you may have, say, 5 jump discontinuities between 0 and 10, and 25 jump discontinuities between 0 and 20, but you cannot have an infinite number of jump discontinuities on any finite subinterval. The total number of jump discontinuities from 0 to infinity or from a to infinity might be infinite, but it can't have too many within some finite interval, just a finite number. We're almost ready to develop more theory, but first we need one more definition. A function f mapping some interval a to infinity into the set of real numbers is said to be of exponential order alpha if exists constants alpha, m, and t such that for t values from t to infinity, we deduce that the function f is bounded by m e to the alpha t. In this case, you can see that the growth rate of the function is bounded by some exponential growth rate. Not everywhere, but at least in the tail. We need a suitable class of functions for which the Laplace transform exists. We are now prepared to write down a theorem. If f, which maps 0 to infinity into R, is piecewise continuous on the interval 0 to infinity and of exponential order alpha, then the Laplace transform of f exists for s greater than alpha. To prove this theorem, we need to show that the integrals defining the Laplace transform converge. So we're going to look at the absolute value of the Laplace transform and try to prove that this absolute value of the Laplace transform exists and is smaller than infinity. Well, this is equal to the absolute value of the integral from 0 to infinity of e to the minus st times f of t dt. By a property of integrals, this is less than or equal to the integral from 0 to infinity e to the minus st times the absolute value of f of t, and because the integral is of exponential order alpha, at least in the tail, we can write this as less than or equal to the integral from 0 to t e to the minus st absolute value of f of t dt plus the integral from t to infinity e to the minus st, and on this integral the function itself is bounded by m e to the alpha t. Now the first integral exists because you're dealing with functions that are at least piecewise continuous, so that you have no worse than a finite number of jump discontinuities on the interval 0 to t, and the function is bounded. So in that case, this integral will exist and be finite. The second integral will also exist, but only provided s is bigger than alpha, because then the last, when you combine these exponential functions, you get e to the minus the quantity s minus alpha all times t. That will only converge provided you get exponential decay, and that happens when s is greater than alpha. And so this will be less than infinity, and that proves that the Laplace transform does in fact converge and give you a finite result. We now know that the Laplace transform exists for functions that are piecewise continuous on the interval from 0 to infinity and also of exponential order alpha. That gives us a suitable class of functions for which the Laplace transform exists. We still need to construct Laplace transforms for a suitable bunch of functions that solve differential equations that we know. So, to that end, I would like to prove the following theorem. The Laplace transform of e to the at f of t is equal to the Laplace transform of f evaluated at s minus a. So you take the Laplace transform of little f, that gives you big F, and what is the effect of the e to the at? The only effect is a translation of the Laplace transform of the function little f. To prove this, we'll just take that left-hand side and use the definition of the Laplace transform. We'll combine these two exponential functions and get e to the minus s minus a t. At this point, you can see that all we're getting here is a Laplace transform of f, but we're replacing s by s minus a, just translating the Laplace transform, and that's the end of the proof. We have to this point had as solutions to differential equations functions of this form, e to the at sine of bt. We can now see that we'll take the Laplace transform of sine and translate it by a units. That gives us b times s minus a quantity squared plus b squared. Another thing that we did to construct solutions was to multiply functions by t, yielding something linearly independent. If f is of exponential order alpha and piecewise continuous on 0 to infinity, and hence the Laplace transform exists, then the Laplace transform of t times f, what is the effect of multiplying by t on the Laplace transform? It ends up being minus the derivative of the Laplace transform of the function f. So the effect of multiplying by t is minus the derivative. It follows by math induction then that if I multiply by t to the n, I'll get negative 1 to the n times the nth order derivative. So this tells me the effect of multiplying by powers of t. I have in my notes here that the proof is obvious, so we'll just take it by ear. The Laplace transform of f is the integral from 0 to infinity e to the minus st f of t dt. So let's try calculating the derivative here. The derivative of f is the derivative of this integral. The derivative may be passed through the integral, and when we take the derivative with respect to s, it only affects this first term because there's only a first factor. There's only an s in that first factor. That gives us the integral from e to the integral of negative t e to the minus st. Remember, we're taking the derivative with respect to s. F of t dt. The negative can come out of the integral here. You can see now that we have e to the minus st and t times f of t, so that's minus the Laplace transform of t times f. And that completes the proof of the first part. The rest of it follows by math induction. We've recently constructed a proof by math induction, so I'll assume that you can construct that part on your own. As an example of an application of this last theorem, suppose that we're trying to calculate the Laplace transform of t e to the at for some a. According to the theorem, this is minus the derivative of the Laplace transform of e to the at, and we already know what that is. That's 1 over s minus a. The derivative then is going to be minus 1 over s minus a squared, or positive 1 divided by the quantity s minus a squared. One of the most important theorems we're going to state is that the Laplace transform of f prime Laplace transform a derivative. This is the reason we're doing this. We're solving differential equations. We need to know the effect of the Laplace transform on derivatives is S times the Laplace transform minus the function little f evaluated at 0. This has the form, the Laplace transform of y prime is S times the Laplace transform of y minus y evaluated at 0. You can see that the Laplace transform of the derivative gives you something where there are no derivatives. We can undo derivatives using Laplace transforms. That's the reason we're going to use this. Well, that's half the reason, as you'll see. The proof is pretty simple. We'll take the Laplace transform of y prime. This is going to be the integral from 0 to infinity of e to the minus st y prime of t dt. To calculate this integral, we're going to use integration by parts, but we need to integrate the y prime factor in order to eliminate the derivative. So u is going to be e to the minus st, and dv will be y prime dt. du is going to be minus s e to the minus st dt, and v will be just y. It follows then that the Laplace transform of y prime is going to be uv minus the integral of v du. We have a minus s that can come out. You get e to the minus st y of t dt. On the first factor, if we assume that s is positive and that y is suitably bounded, then as t goes to infinity, this first factor will tend to 0. And when we plug in 0 for t, the first factor goes to 1, and the second factor becomes y of 0. On the second part, we have s times the Laplace transform of little y. The Laplace transform of little y is big Y, and that completes the proof. As an immediate corollary, and remember, a corollary is a theorem that is immediate consequence of another theorem, we have the following. The Laplace transform of the nth order derivative is equal to s to the n times the Laplace transform of little y minus s to the n minus 1 y of 0 minus s to the n minus 2 y prime of 0 minus the n minus first derivative evaluated at 0. The proof is by math induction. The two versions of this theorem that will be most important to us in this class are the first and this one, Laplace transform of the second order derivative. Our differential equations are typically going to be second order. So we'll get s squared big Y minus s times y at 0 minus y prime at 0. As a simple application, note that if I write f of t is the sine of bt, then f prime of t will be b cosine of bt. It follows that the Laplace transform of b cosine of bt will be s times the Laplace transform of the undifferentiated function the sine of bt minus this function evaluated at 0, and the sine function evaluated at 0 is 0. So this gives us s times, we know the Laplace transform of the sine of bt is b divided by s squared plus b squared. We deduce, therefore, that the Laplace transform of the cosine of bt, canceling the b off of both sides, is s divided by s squared plus b squared. One thing you should know, first of all, you're going to memorize this fact. Second, cosine is an even function, but its Laplace transform, well, the denominator is even, but the numerator is odd. And an odd function divided by an even function is odd. If you replace s by negative s, the negative in the denominator goes away. The negative in the numerator pulls out. So on the whole, you get a negative that pulls out of the entire function, making the function odd. So for sine and cosine, the Laplace transforms of the functions have an opposite, even-odd nature. The Laplace transform of sine is even, the Laplace transform of cosine is odd. Let me put some of these Laplace transforms together in one place so that you can have them in one spot here in the lectures. For the Laplace transform of the sine of bt, you get b over s squared plus b squared. For the Laplace transform of the cosine of bt, you get s over s squared plus b squared. The Laplace transform of e to the at, sine of bt, will be b divided by s minus a squared plus b squared, whereas the Laplace transform of e to the at cosine of bt will be s minus a over the quantity s minus a quantity squared plus b squared. Okay, so I know that there's a long list of functions for which you need to memorize the Laplace transform. Don't worry, I will give you on the exam a table of Laplace transforms, but I don't want you to become dependent on that. You're just going to remember these. One more example. The Laplace transform of the integral from 0 to t f of x dx. We know that the derivative affects the Laplace transform by multiplying by s and then subtracting the value at 0. Here it's going to be multiplying by 1 over s times the Laplace transform of f. And when you evaluate this at 0, you get 0, so we subtract nothing here. So to prove this, recall that by the fundamental theorem of calculus, the derivative of the integral from 0 to t f of x dx is f of t. We're going to then apply our theorem about the Laplace transform of derivatives. The Laplace transform of little f, then, is going to be s times the Laplace transform of the integral from 0 to t, f of x dx, minus what you get when you plug in 0 here, and the integral from 0 to 0 is 0. Dividing by s completes the proof. Next, we're going to talk about inverse Laplace transforms. And so we make a definition. If the function f is continuous, on 0 to infinity, and if big F is the Laplace transform of little f, we say that little f is the inverse Laplace transform of big F, and right little f is the inverse Laplace transform of big F. It is important to know some of the properties of the inverse Laplace transform. So I'm going to write the inverse Laplace transform is linear. This means that 1, if you take the inverse Laplace transform of big F plus big G, you'll get the same thing if you take the inverse Laplace transform of big F plus the inverse Laplace transform of big G. And 2, if you take the inverse Laplace transform of a constant times big F, you get a constant times the inverse Laplace transform of big F. To prove this, we're going to let big F be the Laplace transform of little f, and big G be the Laplace transform of little g, so that little f is the inverse Laplace transform of big F, and little g is the inverse Laplace transform of big G. Recall that the Laplace transform of little f plus little g is the Laplace transform of f plus the Laplace transform of g. Follows then that f plus g is the inverse Laplace transform of the Laplace transform of f plus the Laplace transform of g. A restatement of this last result is that the inverse Laplace transform of big F plus g is equal to the inverse Laplace transform of big F plus the inverse Laplace transform of big G. That proves half of the theorem. Similarly, recall that the Laplace transform of c times little f is c times the Laplace transform of little f, where on the right-hand side we get c times big F. Taking the inverse Laplace transform on each side, we see that c times f is the inverse Laplace transform of c times big F, but on the left-hand side, that's c times the inverse Laplace transform of big F, and that completes the proof. For example, suppose I'm calculating the inverse Laplace transform of 1 over s squared plus, let's say, 7 over s minus 5 plus 9s over s squared plus 4. According to the last theorem, we can do the inverse Laplace transform of 1 over s squared plus 7 times the inverse Laplace transform of 1 over s minus 5, and then plus 9 times the inverse Laplace transform of s over s squared plus 4. According to the results that we've had so far, the inverse Laplace transform of 1 over s squared is t. The inverse Laplace transform in the second term gives e to the 5t all times 7. And the last term, since it's odd, it comes from a cosine, it's going to be plus 9 times the cosine of 2t, b being the square root of 4, or 2. We need some more practice, so I'm going to calculate the inverse Laplace transform of 1 over s squared minus 4. If this were 1 over s squared plus 4, it would be close to a Laplace transform of the sine function, but it's minus, and that means we need to use partial fractions on this. We'll begin with 1 over s squared minus 4 equals something over s minus 2 and something over s plus 2. I bet you can do this in your head. We need the s's to cancel out, so it looks like whatever the numerators are, they have to have opposite signs. We'll need a minus right there. We'll need to get a total of 1/2, so if I put a 1/4 here and a 1/4 here, 2 times a fourth is a half. Negative 2 times negative 1/4 is a half. A half and a half adds up to 1. So that's correct. But let's go back and do this the old-fashioned way. Let's write this out as a over s minus 2 plus b over s plus 2. Clearing the denominators by multiplying both sides by the denominator on the left-hand side gives 1 is a times s plus 2 plus b times s minus 2. If we let s equal to 2, then we'll get 1 equals 4a, and the second factor goes away. This gives a is 1/4. If, on the other hand, we let s be minus 2, then the first term will go away. We'll have 1 equals negative 4b, and hence b is negative 1/4. We can now write the entire expression as the inverse Laplace transform of 1/4 over s minus 2 minus 1/4 over s plus 2. Using the properties that we already know, this is going to be 1/4 e to the 2t minus 1/4 e to the minus 2t. Let's try the inverse Laplace transform of, let's say, 5s plus 3 over s squared plus 4s plus 13. Note that the denominator does not factor nicely, but if we split this and make it plus 4 plus 9, we can rewrite the denominator as s plus 2 quantity squared plus 9. In the numerator, we still have this 5s plus 3. Now, I wish that I had something like an s plus 2 instead of this 5s plus 3. Here's something that we might do. We might write that as a 5s plus 10. When we factor a 5 out from this, we'll get 5 times the quantity s plus 2, which is kind of in the form of something we're looking for. But to do that, to yield a constant of just 3, we need to subtract 7. We can now write this as 5 times the inverse Laplace transform of s plus 2 over s plus 2 squared plus 9 minus 7 times the inverse Laplace transform of 1 over s plus 2 squared plus 9. That last term is not quite what we want either. On the last term, the constant here is 9. The square root of that is 3. What we really want is a 3 in the numerator. Well, we can get what we want. We just have to pay for it. So if I put a 3 here, I can put a 1/3 out front. We have then, as our answer, 5 e to the minus 2t cosine of 3t minus 7/3 e to the minus 2t sine of 3t. You kind of need to understand the rules by which we are operating here. We're trying to get terms in our sums that kind of look like things that we've learned how to calculate inverse Laplace transforms of. I'm trying to make things look like e to the at cosine of bt, and also e to the at sine of bt, and in particular their Laplace transforms, so that we can reverse the process. So we can't just separate things out any old way. We have to separate things out in ways that look like things that are in our table of Laplace transforms. Let's try one more example. Suppose I'm trying to calculate the inverse Laplace transform of s plus 2 over s minus 1 s squared plus 2s plus 5. So we need to split things up using the method of partial fractions, which is really just an algebraic technique designed to split things into simpler pieces. We need this to be of the form a over s minus 1. And since the second factor in the denominator is an irreducible quadratic, we need a linear numerator bs plus c over that irreducible quadratic. Clearing the denominators, we get s plus 2 is a times s squared plus 2s plus 5 plus the quantity bs plus c times s minus 1. We now play the game where we choose strategic choices for s. So if we let s be 1, if s is 1, then this entire second term goes away. We'll have 3 equals 1 plus 2 is 3 plus 5 is 8. A. So A is going to equal 3/8. The second thing we might try is to let s be 0. If s is 0, then the b will go away. We'll have a, which we already know, and c left in the equation. If s is 0 on the left-hand side, we get 2. We end up with 5 times a, which is 5 times 3/8. And then we'll have negative c. If we move things around, note that 2 is 16/8. We'll have c is 15/8 minus 16/8, or minus 1/8. We need one more number to substitute in, and I'm always in favor of choosing numbers that make things simple. There are any number of possible easy choices. Why don't we let s be minus 1? Just because it's easy to calculate with. If s is minus 1, then we get 1 on the left-hand side. Negative 1 squared is 1. Minus 2 is negative 1. Plus 5 gives me 4a, but we already know a is 3/8. And then if s is minus 1, you'll get negative 2 times the quantity c minus b. C is negative 1/8 minus b, the only unknown being b. We'll distribute the negative 2 to both terms in the parentheses. We'll get 1 equals, I'm going to write this as 12/8. Minus minus will be plus 2/8, and we'll get plus 2b. If 1 is written as 8/8, we'll have to move these two to the other side. We'll get 8. Minus 12 is negative 4. Minus 2 is negative 6, so we'll have negative 6/8 equals 2b, or b is negative 3/8. have then a is 3/8, b is negative 3/8, and c is negative 1/8. We now return to the original problem, which was an inverse Laplace transform. We can move the 3/8 out of the inverse Laplace transform. We'll have the inverse Laplace transform of 1 over s minus 1. We'll do the same thing over here, bringing a negative 1/8 out of the inverse Laplace transform, leaving 3s plus 1 over s squared plus 2s plus 5. We still need to do something with that last term. The first term is simple enough. We'll get 3/8 e to the t. We still have this minus 1/8 inverse Laplace transform. The denominator can be expressed as s plus 1 quantity squared plus 4. Divide by 2 and square on that last part. We want the numerator to look like s plus 1. So I'm going to write this as 3 times s plus 1, the thing that I want. That gives me 3s plus 3, which is too much. We need 3s plus 1, so I need to subtract 2. We deduce then that we get 3/8 e to the t minus 1/8 times 3 times the inverse Laplace transform of s plus 1 over the quantity s plus 1 squared plus 4, and then minus the inverse Laplace transform of 2 over s plus 1 squared plus 4. Note that the square root of 4 is 2, and so this numerator is exactly as it needs to be. Finally, we get 3/8 e to the t minus 3/8 e to the negative t cosine of 2t plus 1/8 e to the minus t sine of 2t. Well, I know the figure jumped, but I forgot to distribute the negative 1/8 last time, so there's the solution.